Making that higher place for someone on that. Not behind somebody.
Chemical filter or
Yeah, there is,
oh,
yes, like you pointed
So
out.
recording for us here.
We used to have one, I don't know where it went though.
theories.
Yeah, it's been gone for a
That's
while.
that's how you know that
Yeah.
this is a theory place. Good stick as always.
Yeah.
No, this is good.
This is yours?
This works.
No, that was there, yeah.
I mean, I'm fine.
Yeah, maybe I have some more next time.
Want to introduce? Sure. Should we start?
I think, yeah.
All right, welcome everyone. Very happy to have Yuri visiting all the way from Rutgers. And it's going to talk about long-lived particles in Higgs decays. Take it away.
Yeah, so thanks for invitation. Yeah, it's a pleasure to talk about this stuff. I will it's kind of going to be a fairly narrow focus things, but I think this is kind of an important signature. There's been a, you know better than me, that's been a convergent evolution of different models that goes to the same kind of final state. And this is a really, it looks simple, but it's really tricky because there are 4 particles that get the 125 G, all of the 125 GeV of energy of the Higgs. And you get 30 GeV jets on top of, well, now 50, but in the near future, 200 pileup events, which makes it surprisingly hard. So, and the hardness is actually kind of just evenly distributed along all the stages of the work. It's hard to recognize those events online and write them on tape. Once you have them on tape, they're really hard to reconstruct. And even if you reconstructed them, there are challenges in terms of how you separate them from the backgrounds, right? So I guess this will be a little bit of taking stock of where Atlas CMS and LHCb are at the moment, because these are the only 3 experiments that really do Higgs kind of physics, and what may the future bring. Right, so not that there is no progress, right? So this is from just what, 7-8 years ago, 7.5, right? And that's a slide from the workshop from the long-lived particle community. And so this is on the mass of the particle, a little less than 40, and the lifetimes a little less than 10 centimeters.
I'm sorry, I don't know the notation pi sub v.
So I said it's a convergent evolution of models. So the
Yeah,
pi
I
sum
haven't
v,
followed
so
it.
the pi sum v is the part from the I guess hidden valley, right? So those will be the pions in the hidden valley, and Higgs would decays into pairs of them, and they would go to pairs of p's again, right? So phenomenologically, it looks exactly the same as everything else, right? As the twin Higgs.
Well, it smears out the mass distribution, I guess. Or are they supposed to be degenerate?
Well,
Well,
I mean, they have some mass, right? And they decay into pairs of beads, right? So you still have the four B jets that you have to.
but it's a new particle that we didn't have in the standard model. So in
That's
that
right.
respect,
That's right.
you-
Yeah. That's right.
kind
So
of
this whole thing, I guess you can say that this is your Higgs portal to some hidden
I
set.
just wanted to understand it. And just, could you mind reading the axes?
Right, so because it is kind of the Higgs portal, the long lifetimes of these particles are norm rather than the exception. Right, so this is 1 meter lifetime here.
Oh, that's
Right.
gamma c tau?
Yeah,
Okay,
that's
sorry.
C-tau, right? So this is 1 meter lifetime. So B lifetime in that sense is somewhere here. And then this is half of the Higgs mass. And this is 30 GeV.
And the different colored regions? are
So
just
the,
different
so that
groups?
was the state of the art searches at the time, right? So the Atlas had this way of looking for them in their air toroid, so very large CTAUs. And then CMS and LHCb did searches inside the tracker. So these are smaller lifetimes, but again, limited by the mass and limited by right? So the challenge back then was that, you know, people were seriously thinking if we should give up on this region, which yeah,
So
I'm glad we haven't.
in the diagram that you drew in the first slide, S stands just for stuff or for scalars?
I think it says for stuff.
That's the thing.
So it can be scalar, it can be pseudoscalar, it can be something, right? I mean,
It's the thing that's the pi sub v on the next one.
yeah.
Perfect.
Yeah. So pi sub b kind of suggests that it's a pseudoscalar, right? But they could be a scalar, right? I mean, if it's a in twin Higgs stuff, I guess there's. So so I want to go again through the you know, as the analysis goes on, how do you get these events on tape? How you analyze them, and where the challenges are. Right. So the main thing is, of course, as you know, at the LHC, 40 million events, you know, pin crossings per second, have to select events, and these are really quiet events, right? So these are very hard to pick up at the trigger level, right? So there are several approaches to do that, right? So one was the one that you just mentioned that Atlas have done successfully for many years, right? You try to build a specialized detection in the shielded parts of the detector, right? So if there is this long-lived particle comes in from the detector, explodes in the immune system, it's something very unusual that doesn't happen a lot, gets removed. The same thing has been tried in the calorimeter and so forth, and that's sort of what fuels new experiment proposals like Codex B and Usla. Right? You can, barring that, what are your other options? You can give up on the gluon fusion and take about, that's a big factor that you're losing, right? So if you're doing W Higgs with W decaying to lepton and using lepton to trigger, you lost factor of 200 in your statistics. Right? If you're using Z's, you lose 3 orders of magnitude. But you get something, right? I mean, this is Higgs factory, you're actually getting some numbers from there. You can go and do the gluon fusion, but require Higgs to be boosted so that this 125 GeV becomes a lot of G, right? So actually, ironically enough, this is, as you'll see, is the best result so far that requires huge boost on the Higgs, right? So this is 430 GeV for HT, and HT is the scalar sum of the whole hadronic energy. So this is an about 215 GeV cut on the Higgs PT.
But this is boosted along the beam axis, right?
No,
No,
transfer.
the Higgs.
Yeah, yeah. So
130 GeV transverse moment?
initial state radiation. Right. This is why it's so painful, right? So this is the PT of the Higgs as measured by Atlas. You see that most of the Higgs is produced at 1020 GeV, right? Your cut at 200 GeV PT leaves you all of these events to play with.
That's still cheaper than the W.
Maybe, right? we'll see, right? But yeah, right now, that is the result that beats everybody. Right, so once you've gotten things on tape, your problems are not really over, they're just beginning, right? So Higgs was already a very hard object to find because the cross-section is small compared to the cross-section, right? So if you compare 4B cross-section to the Higgs cross-section, you quickly realize that you need orders of 10 to the 7, 10 to the 8 background suppression, right? And that poses all kind of challenges because human brains are not suited to figuring out probabilities smaller than 10 to the -3, because it just never happens, right? Because you ask, what is the main background to events like these? And it turns out that, oh, well, so this rare things happens, and then at exactly the same point, some other rare things happen. And your first reaction is, well, but this never happens. Well, crunch the numbers. Yeah, right? It's simulating, and Monte Carlo is of very little use because you only can generate so much Monte Carlo. So it's kind of challenging to say that you understand what is the background, right? I mean, you can study the background that you measure in the control regions, but people with good faith can still argue about what it is what that background actually represents. Right? So one of the big showstoppers is the displaced track reconstruction, right? So again, it's not, our detectors are not bubble chambers where you look at them and you see the track, right? You have sparse points, and the sparse points, you construct trajectories and try to point them. And the thing about reconstructing tracks from sparse points is that your combinatorics is huge. And the easiest thing to do is to get you an extra point, which is that track should come from the primary vertex. And then everything goes much faster. But it also leaves you without your signal. All right, so there are some new developments here that I guess especially for Atlas that's been lagging behind for a while. So now they have this large radius tracking that runs on all events. And as opposed to some special streams of things with laptops. You can play some games with the further on, even when you have these large radius tracking as CMS had for a while. I'll talk a little bit about this.
And large radius tracking is something without pointing to the primary.
Yeah, so large radius as in tracks originating from large radius. Right. But even if you reconstructed all of those things, right? Another thing that happens with the displaced tracks is, first of all, you may miss some of the tracking layers, so you don't even have enough, as much track information. And then you don't have the constraint to the primary vertex. So the fraction of misreconstructed tracks is very high, so the background is higher, right? So these tracks are much less pure than the ground tracks, right? And the final complication is this, right? So you think that it's a easy signature, right? So the scalar came down, it decayed, produced a bunch of particles. You just need to reconstruct that displaced vertex, and you're done, right? And this is the plot that kind of refutes that, right? So the problem is that this is a very fuzzy decay, right? So this is not one, but 5 different vertices, right? Because you first get some tracks from the fragmentation, and then 2 vertices from B's and C on one side, and 2 vertices from B and C on the other side.
I think I'm not quite grasping so at the Feynman diagram level.
Yeah.
It's just S to BB bar.
That's right. And that, but you cannot observe naked B's, right? So they have to heteronize.
And you're
Right,
saying
and once
it won't be an exclusive capital B.
Right,
It'll be.
right, so you will have a few tracks from fragmentation, the same way as at LEP, when you collide 2 electrons, you get B's,
Perfect.
and they carry a lot of momentum, but there are some fragmentation. And then B has lifetime, which, it sometimes flies this long.
Right.
And then B decays to D, and D flies also a little bit, right? So these vertices are very fuzzy, right? Nothing here. So if you take all these tracks and try to fit them into a vertex, they won't, right? So this was at some point state-of-the-art search for events like this, and it was a very like tour de force, the beautiful experimental result where people really developed very careful tracking secondary vertexing, right? Because you have a bunch of tracks and you have to iterate which tracks go into the primary vertex, which tracks go into the secondary vertex, how, depending on how they fit together, you discard tracks or add them, right? And was beautiful, right? And you should compare these 2 plots. So this is if this guy goes to a pair of light quarks, right? Which would give you a nice tight vertex. And you can compare like purple and purple because it's the same kinematics. And you see that here you get to the branching fractions of the Higgs of the order of per mil. And it's kind of an order of magnitude worse when it goes to water. And that's exactly this effect, right? That the vertices are fuzzy, right? That you're much more sensitive to the sharp vertices as opposed to the fuzzy ones.
So if S were decaying electromagnetically, like into a pair of photons, for example, should I keep the left plot in mind, like in terms of efficient vertex reconstruction, or
If it decays to,
say a pair of photons, for example, is that much easier than the B's, or?
well, then you have to figure out how to point your photons, right? Because this is not a trivial exercise, right? So in Atlas, there is a finely segmented electromagnetic colorimeter, so you can reconstruct the direction, and maybe with 2 photons, you can try to find the common point, but the precision will not be nearly as good as with the tracking. So the photons is a very different.
Electrons are much easier.
If it goes to electrons, then yeah, this would be nice. If it goes to taus, it also will be nice because it's so tau lifetime is small, so here the vertex will be, tau vertex will be much tighter. Yeah, taus are surprisingly easier than B's. Usually it's the other way.
What determines the branching fraction of the S particle?
It's
call it like
largely free parameter, right? I mean, if generally, right, I mean, in the general Higgs portal point of view, I guess what you're saying is that, the dark matter may not have any standard model interactions, but it should fill our vacuum, and that vacuum is the Higgs, and therefore it should have some coupling, right? But you don't know how much, right? I guess if you go through the survey of the models, I guess it would be interesting to go down to 10⁻⁴, 10⁻⁵, I don't know. 10 to the minus 5 is a good benchmark to shoot for. Ambitious.
So but you're imagining some direct couplings of S2 fermions, or is it just from mixing with the Higgs?
Made from mixing, right? So this is, at least in my mind, I just think about general Higgs portal things. I mean,
But
there are
But if
probably
it's
some
mixing
others
with the Higgs, then you know the branching rate, the ratios of the branching ratios.
Yeah, so you know that it goes, to BB bar.
That's why there's just one vertical axis to worry about,
Yeah,
and it's not a product of.
yeah. So. Right, so then, yeah, this is the kind of, yeah, I think I already kind of said most of this stuff, right? So this is the, how the, primary tracking works, right? So this is log scale of the origin of the track, right? So you see that the regular tracking basically goes down to a couple of millimeters and then plummets. Then you have to go and work very, very hard to regain efficiency. And you're not even getting all the way to 1 or the way to you get here. But even this is a huge improvement. And then you can play games with this as well, right? Because even when you start having some efficiency to the large radius tracks, you can then play this game. So clearly there are backgrounds from random coincidence, misreconstruction of the tracks. This misreconstruction of the tracks can meet an actual interactions of, say, pions with the material of the detector, which produces real displaced vortices, right? The larger your tracking efficiency, the more you know about that interaction, the better your background subtraction, right? So you can kind of do this little iteration, right? So you've gotten some efficiency at the large radius, you reconstructed an object that seemed like it's a promising candidate, and then you can run another iteration of the track finder, only looking from the tracks that originate from that tiny piece of space, right? So that's as clean as doing the primary vertex constraint, but now you have a displaced candidate. Right, so one thing that is kind of a so now in terms of the actual analysis and the results. So this is what I mentioned before, the Atlas idea of reconstructing these decays in the muon system for the large decay lengths. So you see that this is where the Atlas toroid is, so many meters away from the interaction point, and whatever efficiency of reconstruction of things in there. And they've been doing this for a while, I guess since the beginning of the LHC run. They built the dedicated level 1 trigger for it, and it was, were seemingly undisputed leaders in that area. And that's, I think, their latest results. So again, we're kind of, for the C taus of a couple of meters, you're sort of getting to the branching fractions of the 10 to the minus 3. So something that is, getting into the interesting category, right? So, right? So this is one example of how you do the boosting, right? So CMS never.
Your question made me think harder and I realize that I'm confused about the following. You treat C tau as a free parameter that's independent of the production. But if really you're saying the only parameter is the coupling of that everything is going through the Higgs, so there's one parameter, which is the coupling of this S to the Higgs. Or the mixing, I should say. Why is C tau a free?
Well, because you don't know how big that mixing is. I think there is a general tension, right? So Josh wants to say something.
I think they're not assuming it's only the mixing. I think
Oh, okay.
you could have a free gluon coupling, like it couples to heavy colored things, for example.
Yeah, no, I can imagine a much more
Yeah,
general,
and you could have approximate, I think it's stable because there's an approximate Z2 symmetry. So the
anyhow.
But in the
certainly
simplest
phenological-
case, if it's like Higgs squared, singlet squared, right, then the strength of that coupling allows you to determine C tau, and then you know the lifetimes to all of the fermions. So it's a 1D parameter space, not a 2D.
sure.
So there's something else, some other free parameter somewhere that makes it a 2D parameter.
Unless
Sure.
somehow phenomenologically, they just act as if they're separate measurements and
Yeah, I don't think they have in mind the one.
Yeah, I mean, it doesn't cost us much to treat the C tau as a free parameter. And yeah, I think I'm trying to remember now.
it still seems wrong to call it sigma though in that case, because it's sigma times a branching ratio into BB bar, for example. It would be something like that that really gets plotted. If C tau is, if you don't make that extra assumption, then I think what you're measuring
Yes.
isn't just sigma.
Yeah. So in the end, what we're measuring is sigma of the Higgs going into 4Bs.
Right, so it's really
From
sigma
existence.
times the branching fraction.
yeah.
Sorry, I apologize.
No,
I'm just trying to catch up.
No, it's fine, right? I mean, from my experimental perspective, right? I mean, the way, I've always operated is that, I never really trust a particular theory model, right? But you sort of, if you survey enough of them, you can kind of see the trends, right? And this
Probably
final,
shouldn't call
yeah.
it sigma, and you should call it sigma times B, probably. But anyway, that's can be discussed later.
yeah, I think,
Oh, wait, there is a times B in that.
yeah, there is a time.
Some of the plots, I don't think it was there, or maybe I just didn't see it. Sorry.
Right, so this one was is a case for how using boost actually helps, right? Because this is CMS detector. CMS has a very different immune system. It's filled with iron. There has been no trigger like this that selects the decays in there, right? And then it still turns out, very surprisingly, that you can trigger on the missing ET, right? So it's the same thing as boosting the Higgs, right? So if the Higgs goes away, Higgs decay products go away from and only appear in the immune system, then you're missing that momentum, right? So this is really the PT of the Higgs cuts, right? So it's again about 200 GeV that I mentioned. And you'd think that you lost tremendous amount here, but it turns out that the iron in the immune system actually helps here, because in Atlas is an airteroid, they can measure beautiful tracks, but there are not that many tracks in the Higgs decay, right? So if you have pions that induce hadronic showers, then you have a huge multiplication factor, and you see a lot of hits, that you sort of see a cloud of hits following the path of the Higgs, right? And you can construct an offline analysis with it. And in the end, you get to the point where you're actually very competitive with the Atlas measurements without even a dedicated neon system. Right, so this was a very interesting, the first very non-trivial lesson about the boosting of the Higgs that I found looking at this type of finite states. Right, so again, so something 10 to the minus 3. Right now, we actually do have a muon trigger, a trigger on the events like this. So this result should improve tremendously next time, in the next year or two. Right, and then finally, you can, if you want shorter lifetimes, you need to look at the decays on the track, right? So this is an old result, but it's kind of shows you where people start from, right? So you get this fuzzy vertex, you get this hard to reconstruct tracks. So people go and, what physicists do. Physicists invent smart variables, right? So they look for things like what if we measure the jet in the calorimeter, what fraction of its energy comes from the prompt tracks that we can reconstruct well, right? So if it's a large fraction, then it's likely wasn't a displaced decay, right? If it's a smaller fraction, then it could have been a displaced decay. And then you can also look at the angles and different kinematic variables. Like this, between the jet and the innermost hits of tracks. That was very clever. And you go and you come up with some cut-based analysis. So this one for the entire run 2 only reaches to kind of a few percentage type territory. Right. So these are really hard things to reconstruct. So if you go to, so this is more recent results. So this is the Atlas after they introduced this larger radius tracking, right? So it's still smart variables for the jets, but they made a multivariate analysis out of them. And, they find it useful to have this material veto because in their interpretation, they're still dominated by the interaction with the material. Right, so you're producing an isolated pi, and the pi slams into the tracker. You go and have yourself a displaced vertex. You reconstruct a couple of tracks, and that vertex is now looking fuzzy. Right? So that's kind of a picture that they get when they look at these the map of these secondary vertices, and this really tracks with the number with where material is. So you do all this, right, and you end up with the limits, which are kind of a little bit better than what I just showed for CMS, but still kind of order of the 4 or 5%. One thing that you can clearly see here, right, is that once you go and do that vertex reconstruction, right, using the large radius tracking, it improves your sensitivity to the low masses, right? So you see that this is the lowest mass, and it's kind of in this. So all these curves correspond to different scalar masses, and they're all kind of tightly grouped together. Whereas you really lost a lot of efficiency for the light ones in a more crude analysis. Right. So if you don't do just Z, but also do W's, well, and not to sacrifice 3 orders of magnitude, but just 2 orders of magnitude, right? You get much better, right? So this is the latest from Atlas here with the W's and Z's. And so again, this is W. So 1 lepton here in this plot is the W, 2 lepton is the Z. This is vector boson fusion for the Higgs production. And again, the W and Z for more and more ambitious vertex requirement. And yeah, you kind of see that your main sensitivity where you have some events come from places like W. That's here. Okay, so that's that, right? You think that this is the best you can do, right? So, oh, right. So this is their final results, right? So yeah, if you 10 to the -4, right? I pretty much said all of that, right? And then again, looking at the Higgs PT distribution, you think that boosting the Higgs is useless. Turns out, not so much, right? So you go and you trigger on the HT, highly boosted Higgs. But then you go and play this game, right? When you reconstruct all the little displaced vertices and you try to associate as many of these little vertices to jets, and you go and train big neural networks that somehow go and instead of invent their own smart variables that are hidden inside that neural network. And there is a fairly easy way to come up with a background measurement method where you have 2 fairly uncorrelated neural networks, and you can play one against each other in terms of the background determination. So that one all of a sudden goes and gets you way below 1%, right? So you see it all for Higgs, it reaches a few 10 to the -3, right? So we got an order of magnitude better result from the boosted Higgs, despite much higher hit in the statistics. Another interesting thing that you can look at, if you concentrate on the green line here, which is 30 GeV mass, you see that there is absolutely no difference between fuzzy vertex and non-fuzzy vertex, right? You get about the same. Right, which tells you that you're kind of approaching the optimal utilization of all the experimental information, right? So you're not losing something because you haven't been smart enough. And again, taus on one hand are easier, but there are fewer tracks here, and they're still harder to reconstruct statistically, right? But you still kind of, for the first time, I think, in the area of below 10%.
Just out of curiosity, what's the G and GNN?
Graphic.
Oh,
It's
okay.
a graph neural network. So this is like the latest and greatest.
Yeah, no, I just.
Right, and no, but this is actually an interesting case because this data structure actually lends very well to the graph neural network, right? Because the graph neural networks, you have your nodes and your connectors, right? And here you have your tracks and the vertices that they form. So this is actually, unlike many multivariate things in our field these days, this is actually well motivated and executed. Right? So this is kind of what you, so an interesting thing about the analysis that I just showed, this is actually run 3 analysis, right? So it's very recent data, and it is less than a third of the run 2, right? And you can see that this was analysis with from run 2, right? That was this very careful adaptive vertexing, right? And you get this much improvement with less data, right? And at this point, again, you can go and try and interpret this limit in particular models and start actually making a reasonable limits to models that predict whatever electroweak phase transitions. Start excluding parts of parameter space of those wasn't. I think that's pretty much, the level of the branching fraction that you have to do to get on these plots. All right, so this is, I think, the current state of the art, right? So you see this. So this is split between very light scalars and heavier scalars. Lighter scalars are also harder because if they get boosted in the Higgs decays, then you don't resolve 2 jets, right? So you don't really have 4 displaced jets, you have just 2 displaced jets, right? And then, yeah, so this is the boosted Higgs analysis. This is the Atlas's W Higgs. They flip as you go to the lower masses, right? Very predictably, because this is already boosted Higgs. And if you go to the small scalars, they become completely squished together. Right? So, however, in defense of this, right? So this still is, in my mind, has some room for improvement going down here, because even the state of the art thing relies on kind of smart variables and PDT of the smart variables, right? So it's the thing that I repeat to my students these days is don't send a human to do a machine's job. And, increasingly, this type of analysis are more and more machine beats the human. All right, so clearly one of the challenges, frontiers going this way, right, is so this is high PT Higgses, these are low PT Higgses. There are a lot of lower PT Higgses which are boosted just a little bit less, right? And it would be nice to include them as well, right? So that push to reconstruct lower PT displaced jets, I think, is the sort of this frontier that we need to get to, right? And as you go to the lower and lower PTs, you basically the main thing that you lose is calorimeter information becomes less and less useful, because the fluctuations of energy from the pileup are so huge that the jets, especially at low PT, become pretty much soft jets. So the thing that I think is being developed very intensely is this: you completely forget about everything except the tracker, and you just zoom on these secondary vertices, try to get as much tracking information as possible. Right, so there is one result already out of this, right? So CMS in round 2 did this thing called beep parking, right? It was supposed to help measure, elucidate one of the LHCb anomalies with the RT star or something like this, where they just saved all the events with the low PT displaced muons, right? There are a lot of them, and you can't reconstruct them in real time, but they wrote them on tape during the run, and then once the run is over, you have all this computing power that you can use to reconstruct them, right? And it didn't really work very well for p-physics purposes, but it works really well for the 4Bs, right? Because if you have 4Bs, you have about 40% probability of having at least one muon in their decays, and if it's displaced B decay, these muons are going to be displaced, right? So it actually turns out that you get in the Spark data, you get about a quarter of the total data analysis, and you can set the limits. So this is just a few, on the order of a couple of percent, but this is for this very low mass that I mentioned that is very hard to get, right? So this is a fairly competitive measure limit for with these fuzzy vertices reconstructed with a machine gotten from the parking data.
So the 33% of burn is just how long they had this on for.
Right. So the way this B parking works is it's not on. You're not writing data all the time, right? There's only so much bandwidth that you can actually do this, right? So and the luminosity starts high, and then you kind of drop. And as you were dropping, right, you were switching these things on and writing them out.
I see. So it doesn't scale well to the future.
Yeah, right. So I think for run 3, there's luminosity leveling, right? So now you get a fairly uniform rate throughout the fill. But they solved some of the data issues, right? So now you write some parked data. You're still parking some data, and that would be without the loss.
Why wasn't it useful for the B-main comments?
Because remember, this is this RD RK things, right? So you need to measure both electrons and muons, and electrons are tricky to measure, right? Because the electrons are not very IPT, and there's like up to 2x knots of material on the tracker, and they scatter like crazy, and they're hard to identify, right? And the original projections of what the efficiency should be was about an order of magnitude more optimistic than. So yeah, right. I mean that's but we now use it for much better purposes, while these anomalies die on their own by other means. Okay, so this is where this is right. So run 3 now is our playground to understand how to push Higgs reconstruction into low PT and low lifetime frontier. So what would happen at the upgrades? Actually, how am I doing on time? I'm 10 minutes. Okay, so in 10 minutes, 10 minutes. So and this is purely in CMS, right? So this is why it's exciting to do high lumis. Think about high lumis stuff if you're at CMS. The CMS will have track reconstruction at level 1, right? So this is really a revolutionary thing for many reasons. So this is also going to be the first time that the silicon detector at Hadron Collider is used as a trigger device. And the reason it never happened before is that there are so many particles flying by, there's so much data that even a simple act of just taking all the hits and transmitting them to the building that houses your electronics takes longer than you can afford to build the trigger, right? So this is actually some of the interesting things about the upgrade business, right? So when we were designing the upgrade for high Lumi LHC, there are some really like immovable design parameters, right? And one of the immovable design parameters was the size of the hole from the cavern to the auxiliary cavern, right? Because you can fit only so much fiber into that, right? And so the way CMS is able to do this is because we found a way to cut down the information by a couple of orders of magnitude. And you do this by doing this trick, right? So our tracking modules are actually not just a tracking detector, but two tracking detectors close together, right? And you can correlate the two of them right there on the module. Right, so basically you measure that angle at which track is crossing the module, and then if the angle is like this, it's from high PT track, and if the angle is like this, it's from low PT track. And you got your 2 orders of magnitude reduction in the number of hits. So this is great. I mean, this is, if you think about this, right, it's still awe-inspiring thing. Right, so at the high Lumi LHC, every track above 2 GeV will be reconstructed, like from every collision, right? Which is really, at least for me, for me 10 years ago, it would sound like science fiction. Well, 15 years, that sounds like science fiction. The interesting thing about this is that, right, so this is pretty much the same plot, right? So imagine that these are the 2 layers, these are your 2 tracking detectors that you correlate. And then this is your hit in the inner plane, and then this is your plus 2 GeV track, minus 2 GeV track, right? So any hit between these 2 points will tell you that, okay, high PT particles came here. But this configuration of hits actually allows for reconstruction of the track, is sufficient for displaced tracks, right? For some displaced tracks, right? So this displaced track, for example, will be reconstructed. This clearly wouldn't be reconstructed. You can actually make a 2D plot of this, right? So depending, and it's sort of gets easier and easier as you go out in radius, right? Because your impact parameter, the distance from the interaction point comes divided by the radius of your tracking layer, right? So even in the layer 1, you can still kind of get a couple of centimeters of efficiency of the displacement. And then if you go and you can start going through simulation and see if you can run it, make a tracking algorithm that would reconstruct your displaced track, right? And that, if you could, then, whether or not you can compete with the WH, right? And reconstruct this gluon fusion produced Higgses and not do the Ws. And the answer turned out to be yes, right? So we had like a little toy simulation where, this kind of curves is what you get from such displaced track trigger. This purple line is so this is the number of events signal events that you trigger on, right? So you see more than factor of 50 below is the W Higgs, and you're comfortably beating LHC, right? And then we had the more, CMS blessed simulation with the improved chant and everything. still see that you get a lot of tracks with this displaced tracking algorithm compared to the case where you're not. Right, again, with the trigger, it's even more important to know that your displaced tracks are much less pure than the prompt tracks. Right, so if you like by the numbers, if you have a displaced track, it's a fake. Right? How do you reduce that on the trigger level? The only way you can do is the way this works is that, so you have like 5 parameters of the helix, like inverse PT, rapidity, phi, and 2 displacements. Right? And the way fake tracks work is that they produce approximately uniform distribution in all 5 parameters. So if you see 2 displaced tracks that go in about the same direction, that's an indication that maybe something interesting is happening, right? Because otherwise that'd be completely uncool. So that what helps with the Higgs studies, because then you have an actual B-jet, so you have several displaced tracks going. There is another way to deal with this, which is if you ask things to come from the same vertex, right? I think I'll show you. Yeah, that's actually, it's not quite in the Higgs decays. It's maybe still Higgs portal, but it's long-lived particles in Higgs decays, right? So again, you can see that if you had a particle here, it came here, decayed to 2 muons, right? Then you have 2 displaced tracks, and most of the 2 helixes will cross in an XY plane, but then they will not cross in 3D, right? And you can see that these are the real particles and these are the fakes, and this tail goes way. The same way, these things will be pointing back to the origin, right? Both the fakes are going to be having a long tail this way, right? So this is basically, it's not really, all these blue stuff that gets rejected is not the physics background. It's really this combinatorics that you're playing with to clean things up. All right. And again, right, I mean, so you'd think that for things like this, where you have a B meson that goes to this long-lived particles and something else, you think that the LHCb will be a dominant force. Well, we'll see what in the end will be a dominant force, but CMS can still go, and so based on the particular model, for a couple of different scalar masses, you can see that there is a region of parameter space where we'll be beating LHC at some point. Maybe I should skip the thing about the LHCb. And then, yeah, right. I mean, another thing that sort of closing the loop back to the largest lifetimes is Methuselah, that I hope will eventually get built, not in this variation of the full thing, but even a small and cheap thing is also, you're getting into the 10 to the minus 5 type of branching fractions for the.
Are there still prospects for even a small cheap?
Right, I mean, if Henry wasn't Henry, and they went for this type of device, they may have been yeah, right. It's their cost really goes as per square meter, right? So yeah, the 20-meter one costs just a few million and fits into this agile project. Right, so you're still probably, our problem is now we're still in the worst funding scenario so far, right? Because we're below inflation and the CHIPS money didn't come. Yeah, you still want to build little DMX first. But yeah, this is doable. It's not that much. Right, so, yeah. If you don't concentrate on this and just look at this curve, it actually looks fantastic. It beats the Codex B most of the places. And then, as you can see, where Codex B works better than Medusa, you can kind of get. So this is an Atlas plot, so it only has Atlas limits for the muon system. But you saw that the CMS ones are coming in here as well, and this will get progressed, right? So actually, as things goes on, it looks like Codex B will be less useful than combination of Atlas CMS. So yeah, I guess that, that brings me to the end, right? So I really, at least for my tastes, this seems like a final state that really is worth digging into and cleaning up as best as we can, right? And this is one of the most interesting application of the high Lumi LHC, because high Lumi LHC is a Higgs factory, right? I mean, it's not an artisanal shop like an ILC would have been, right? It's big, it's noisy, it's dirty, and it produces a whole lot of Higgs. Right? So by the end of the high Lumi LHC, we're gonna have 200 million Higgses per experiment, which is not a lot of Higgses, right? And the longer we look at it, the better it turns out we can do, right? So again, even compared to 6-7 years ago, fast deep learning bump to everything, we're still finding huge improvements. Right, so yeah, this area that we were ready to give up on 8 years ago, I think we'll get covered.
I have a theory question. I don't have the numbers of the Higgs portal stuff at my fingertips. But is this looking under a lamppost, or is it really compelling? So this is sort of a weak interaction, old-fashioned weak interaction pion decay kind of lifetime regime with much heavier masses, but correspondingly. I'm just curious.
I've been doing searches of this.
I mean, not to say it's not
No,
absolutely valuable, but I'm just curious.
But I had this lamppost joke in every talk that I had, making a case for detector and trigger improvements that could label something
Well,
like
no,
that.
I'm sorry, I came across.
No.
I think it's absolutely necessary, but still, there's some sort of theory landscape. And in the theory landscape, is this a place we should be like expecting there might be some discovery, or?
I mean, you should ask Josh.
Well, it was,
but,
yeah.
but,
What's your opinion? If you had to place money on where this would be, if there's a true Higgs portal, where would C tau be, for example?
I mean,
What would be the wrenching fraction?
sorry, you're at the
I wanna
CTOW
hear-
branching fraction. Yeah, I mean, having long lived is okay, it's reasonable.
It's okay, but I'm saying if it's doing all the jobs you'd like it to do, I don't know, maybe it's dark matter, maybe it's baryogenesis. What jobs put it here?
Well, it's not dark, S is not dark matter here, right? With
No,
these
but
things.
as a portal, maybe it's
The
relevant.
baryogenesis isn't so related to the lifetime, I think. It's a big change.
Yeah, from what I understand, from the baryogenesis models, these are all lifetimes and masses are just free parameters from what theories.
So basically, it's looking under the lamppost. I mean, there's not like you would say, oh, this is gonna rule out.
But I
Some
would say like the quadratic Higgs portal is a very well motivated, renormalizable interaction.
Totally.
Yeah, so I have
H
to
squared,
say
S squared.
H squared S squared. So yeah, so given a mass of S, what's the value of that, cross quartic coupling that you constrain with these plots? That I don't have a good answer for it, but that would be
That would be the way
interesting.
easier
Yeah,
to think about.
right.
Did you have
Right.
that plot? Or maybe Josh can do it in his head?
Yeah.
Josh.
That doesn't tell you the size of the HS mixing, does it? Cause you're saying SVEV, free parameters.
So this is a question
but-
that I asked many theorists
It tells you
many
that-
times,
So
right?
it does tell you the H S squared vertex, because you have an insertion of the Higgs Vev, and that gives you a
Right,
linear
that relates to
graph.
H squared, S squared to the H, S squared. But then you care about the HS mixing, which breaks the S2, Z2. Which is another parameter, right?
I'm sorry, I'm just
Right.
being very silly, like you have regular, whatever, the Higgs production, and then the Higgs can decay to two S's via the, H squared S squared with the insertion of the Higgs, so I feel
Oh,
like-
sure, for the Higgs branching fraction, yeah.
But yeah.
And yes, lifetime is a dependent parameter.
Oh, yes.
And which is some weak breaking of the SC2 symmetry.
Yeah, right.
I don't know, to me, I don't take the model that seriously, but I think that it could capture other models in the same, if you have a tens of GeV thing with the order tens of centimeter lifetime, it's a pretty wide net, I think.
Oh, no, I'm not saying it's not interesting.
Yeah.
There's this spectacular that you can do it. I mean, who would have ever believed it?
I
But,
wouldn't.
That's really impressive, but I'm just curious, where is the regime that of interest, and there's not a
But
particular
indeed, but
answer.
then, yeah, Josh is right, so
Just-
the quadratic Higgs, it's not a 1D parameter
Right,
space, because
right.
you need to break the Z2, so. But
And-
there's still the SH squared coupling and the S squared H squared, so that's a 2D parameter
Yeah,
space
yeah.
plus a mass for S.
And I
Yeah,
guess the
yeah.
question would be,
Yeah, I'm not sure how
make
to
some
project
plot
it.
of where in that parameter space do you solve some interesting theory problem.
Yeah,
And
Well,
how
so,
does this-
I mean, I guess the only plot that I have like on my doc right now is sort of this, right? So for one particular model at least, you start getting into parameter space that would have done something good for baryogenesis.
Where does that lie? I'm just not that up on.
Right, so
Models.
there are I'm not taking any theory models very seriously, but there are two parameter model, two masses in the model. And I think it's baryogenesis happens pretty much everywhere in this plane, and we already exclude part of it.
So you say that anywhere in that plane is equally good for baryogenesis? And you're
That was
cutting out half
that
of
was
it.
my impression from.
Yeah, I'm not sure.
I
if it's
would
specific,
need to. I
but
would need to
definitely,
look
if
at
you want a first order electric phase transition, then Higgs mixing size one with a scalar
Has to
is
be
well
fairly
motivated.
system.
And
But then you need it to be fairly strong, don't you?
the Higgs scale, yeah, you need to have a big
And
effective
then,
Higgs
then
potential.
I would think you would. Yeah, it's just, I thought maybe you knew it. Okay,
I don't.
I guess for, like, you talked about two displaced vertices. If you were to do like a single displaced vertices, then there are, I think, quite a strong motivation for like these heavy axion models people look into. So you would produce like axions in glue fusion, just like the Higgs, and the axion could be somewhat long-lived and then decay to pair-based things. So there, like in some part of the parameter space, you could solve the strong CP problem. So these are much heavier than the standard HC reaction, but then there is connection to these theory questions.
But that's sort of a different
Right.
final state that
Yeah,
will
of course.
that we could still be sensitive to
Yeah,
in these, in the context of these.
So is there a lot more that can be done with parking, like, moving forward, like besides this one B?
I mean, so I think right now there is now an exotic, at least in CMS, there is several exotic streams. Right, so the displaced muon stream is now much more exotic than it used to be, right? Because it was going high on the BT and low on the impact parameter. And that's not what you want for exo. You want a higher impact parameter and the lower BT. Right, so that is there. There are some there are some tau related things, I think, that are getting parked. And then scouting gets more important, right? So scouting is a separate way of dealing with the with the trigger. So so there are two layers on the trigger, right? So one is electronic when you do the first reduction of the data. And then you actually attempt full event reconstruction, right? And then tiny fraction of the reconstructed events you can actually write to tape. But instead of writing like a megabyte, couple of megabytes of data that you can write, you can just record the result of that reconstruction that you did. And that's just kilobytes, right? And that gives you imperfect calibrations and bad resolutions, but you get the events.
You're stuck with this.
Right. So, like, we now see, so Ahmed that made this scouting tau stream, and I think he now has 2 or 3 more order of magnitudes more Z to tau tau events than the standard people. So yeah, you're going to see a few very cool results with low PT tau.
No more questions, thank you again.
So far, we're good.